Okay, now we're going to talk about some applications. Probably one of the most well-known applications to quadratic equations is gravity, and we've got a couple equations here that invoke gravity. In fact, they come from force equals mass times acceleration. If you solve that equation without any kind of air resistance, then you get the following equations above. And so let's apply these equations. Let me also talk about them. H of t, this is function notation. This is height as a function of time equals this polynomial over here. You see that we have time showing up here, which is squared, time over here, and then this, some kind of initial value. What this says is negative 16t squared plus v naught t plus h naught. Some people say v0 and h0. I like v naught and h naught. What v naught is some initial velocity, and what h naught is some initial height to begin with, okay? Now for this equation on the top where you have a negative 16, that comes from the acceleration of gravity in feet per second squared. And so that means that this velocity has to be in feet per second, and this height is in feet. Overall, if we were to plug in a time and an initial velocity and initial height, we end up with a height in feet, okay? The second equation applies to the metric system, meters per second, okay? So the negative 4.9 comes from half of gravity. Gravity is negative 9.8 meters per second squared, the acceleration due to gravity, that is. So in this case, this v naught would be in meters per second, and this h naught would be in meters. And so it just depends on whether you're talking feet or meters for which equation you're going to use. And let me just give a couple examples using both. Let me start with an example of kicking a soccer ball, and I'll use the metric version in honor of soccer around the world. Okay, so this marker is not doing me justice. There we go. This one's a little bit better. So here's our soccer ball example. Soccer ball, which is just sitting on the ground, and somebody comes up and kicks it as hard as they can. And now we have an equation that represents the height of that soccer ball over time and looks like this. The height, I don't have to put of t, I can just say the height is equal to, I'm going to approximate this as negative 5. Instead of the negative 4.9, I'm going to approximate it as negative 5 t squared plus 35 t. Now notice I don't have a third part over here. That's because the soccer ball is on the ground. And so the initial height is 0. That term is not there. So the height at any time can be given by this equation. Okay. So what if I were to ask you, somebody comes up, they kick the soccer ball. When is the soccer ball going to hit the ground? So the first thing we should recognize to solve this problem, when is it going to hit the ground, is that h equal to 0 is the ground. It starts at 0 before it was kicked. It's going to end at 0 when it hits the ground. Now, I'm not taking into account all this bouncing and all this other stuff, just when it hits the ground the first time. Okay. So if I want to solve when it hits the ground, I'm going to put the 0 here in my original equation and say 0 is equal to negative 5 t squared plus 35 t. And I am going to attempt to factor this quadratic equation to solve it. There is something I would do right away, and notice that there is a greatest common factor of 5. So you can factor that out, or you can divide everything. I would divide everything by, in fact, negative 5 as a personal choice. You got to do it to the other side of the equation as well. 0 divided by anything is 0. On the right side, this just gives me t squared. 35 divided by negative 5, negative 7 t. Okay. Now what's nice about this is we can simply factor out the t in the next step. So I've got 0 is equal to t times t minus 7, and then use the 0 product principle from here. So now I'm going to say, okay, 0 is equal to t. That's one of my solutions. The other one, or 0 is equal to t minus 7, add 7 to both sides to solve this equation, and I get 7 is equal to t. And before I fully answer the question, which is when is this ball going to hit the ground, I should remind myself that I'm bringing math into the physical world, answering a physical problem, and so our mathematical solutions must be constrained to the physical situation. In other words, at t equals 0, yes, the ball was on the ground, but that was before I kicked it, right? When is it going to hit the ground? At 0. No. So this one doesn't count as one of our solutions. Suffice to say, that was not when it hit the ground after I kicked it. This one is okay, 7. So I'm going to say, when did the ball hit the ground? 7 seconds after I kicked it. And there's our physical solution. Let's take a look at another example involving gravity. How about one where we drop something off of a building? Who hasn't wanted to do that or done it? So let's say we've got h is equal to negative 16 t squared. And since we're just dropping something, I'm not going to put any kind of initial velocity on this. I'm just holding it out and then letting it go. So the initial velocity is 0. There is no v naught times t term, but let's give it an initial height plus 121 feet. I'm using the equation in feet. We're at the top of a building at 121 feet, which is maybe strange. Who knows why they did it 121 feet. But let's ask the same question that we asked about the soccer ball. I drop something off this building. When will it hit the ground? And this question, I should also say, is neglecting air resistance. So if you drop an ant off a building, this equation is not going to work. If you drop a bowling ball off the building, this equation is probably pretty accurate. So let's take a look at what we would get neglecting air resistance again. When would this thing that I'm dropping hit the ground? Let's say we're dropping a bowling ball. In extremely safe conditions with nobody around, right? Okay. Maybe we should drop something else. When will it hit the ground? The ground is 0 for h, so I'm going to say 0 is equal to negative 16 t squared plus 121. And I'm going to ask myself if there is any way I can factor something. I could divide by negative 1 just to make this positive in the front here. And that would give me 0 is equal to 16 t squared minus 121. And that did something nice for me, at least in terms of recognition. Perhaps this is a difference of squares. And in fact it is, because 4 squared is 16. That means 4t quantity squared is 16t squared. 11 squared is 121, so I can say, oh yeah, difference of squares, this must be equal to 4t minus 11 times 4t plus 11. And all of that is equal to 0 still. I can set each one of these equal to 0. 4t minus 11 equals 0, or 4t plus 11 is equal to 0. And then I solve both of these equations. So from the one on the left, I can add 11 and divide by 4. Add 11, add 11. Over here, I'm going to subtract 11 from both sides. And let me just retype my equations up here, reprint that is. This gives me 4t equals 11, or the other one is 4t equals negative 11. Divide both sides by 4. Divide both sides by 4. And so the left equation produces t is equal to 11/4. The right equation produces t is equal to negative 11/4. And we can say something right away. We're looking for a time when this is going to hit the ground, and So far as we know, time cannot be negative physically, so even though that is correct mathematically, we're going to get rid of this one. We can say that that one is extra or extraneous for a big long word. So when does it hit the ground? 11/4 seconds. That's kind of a weird way to say it. So 4 goes into 11 twice. That gives us 8. 3 left over. Put that over a 4. Ah, that looks a little better. When is it going to hit the ground? 2 3/4, 2.75 seconds. Again, do not drop a bowling ball from a high building without extreme precautions. Let me move on and give a couple more applications and then perhaps talk about complex solutions in some other examples.